All right. Last chapter. Chapter 9. We're going to start with the Laplace transform. So the definition of the Laplace transform. If let f be a function defined on all positive, right, from 0 to infinity, the Laplace transform of f is written with this like fancy L of little f. It's equal to capital F. And it's defined as an improper integral where Laplace transform on little f of s is going to be big F of s, and it's equal to the integral from 0 to infinity of e to the negative st times f of t with respect to t. Where the improper integral converges, then f of s, this Laplace transform, exists, and it's usually for s greater than some value. And in general, we write that the Laplace transform of the lowercase function is equal to the capital letter, right? So little Laplace of little f is big F and g of g and all that. All right, so let's just start off with doing this. Why are we doing this? Because the Laplace transform is another strategy to solve these differential equations, and especially ones that are very tedious in nature to solve on the right hand side and stuff. So this ends up making life much easier, especially with a lot of real life applications in engineering and stuff like that. So all right, so I'm gonna write that again, the definition of the Laplace transform, which is L of little f of s is capital F of s, and it is the integral from 0 to infinity of e to the negative s t times f of t, and all of this is with respect to t. My grandpa worked for Lockheed for years, and he always did that to his s's to make sure that they didn't look like fives, I guess. I don't know. He was super old school, but not a bad idea, right? You don't want to confuse your s's with fives later on. That would be a nightmare. Okay, so let's just straight up practice using this definition. Yeah, so we're going to use the definition to find the following. So use definition of the Laplace transform to find. We're going to start with e to the at. Yeah. All right. So this guy, using this definition, is going to be the integral from 0 to infinity of e to the negative st times f of t, which is this e to the at, and then dt. All right. Well, we've got to integrate this guy. But do you see, you got both of these are base e, and you're multiplying. So this is equivalent to e to the, they've also both have a t. So it's like e to the negative st plus at. So if I factor out a negative t here, I would have an s minus a and then dt. Yeah. Hopefully you see how I got that. All right. And then this is an improper integral. And remember what we would do is write, this is the limit as b goes to infinity of replacing that infinity with b, and then 0. And negative t plus minus a dt. Okay, so now when we go to take this integral, remember this is with respect to t, so both s and a are constants. We're integrating this with respect to t, so this is actually a pretty easy one to integrate, right? The antiderivative of e to the negative t is just e to the negative t. Anyway, so this ends up being the limit still as b goes to infinity of, now this would be e to the negative t, s minus a, but then chain rule would have said times negative s minus a, so we need to undo that. So it's divided by, or multiplied by 1 over negative s minus a to undo the chain rule. And we're evaluating that from 0 to b. Now, you're plugging these guys into t, right? That's because it was with respect to t. So we're plugging it into t. And this is an e to the negative. That's super important because it's like 1 over e to the t times s minus a. And maybe you want to write it like that, so that way it's obvious to you. When you've got a negative here, and then you're plugging in b into this, right? So now you've got an e to the b times some constant. As b goes to infinity, you're dividing 1 divided by infinity. So that zeroes out. So it's important that this b is still a negative there. So this ends up being 0 when you plug in the b, because you're taking the limit as b goes to infinity. And then plugging in a 0 into here, you get e to the 0, but then times this guy. So it's a minus, and then you're left with a negative 1 over s minus a. Yeah. And so you end up adding those guys, and it's 1 over s minus a. You do the Laplace transform on e to the at, it ends up being 1 over s minus a. Now, keep in mind that if we have to put a restriction on this, s must be greater than a. Because if s is not greater than a, then you would have a negative value here. And if this is a negative value, right? Or even, yeah, right here, if this is negative, if s minus a is negative, then e to the negative t times the negative ends up being e to the t, and you've got e to infinity, and so it does not converge. Does that make sense? So there is this restriction of s must be greater than a here, because if it wasn't, it would be a negative number, which then when you're plugging in infinity, well, we don't plug in infinity, but as we're taking the limit as b goes to infinity here, you need that to be a negative for that to zero out. Hopefully that made sense. Okay, let's also do, using the definition, we're going to find the Laplace transform of what? Of t. Okay, so using the definition, we've got from 0 to infinity of e to the negative s t times t, and then dt. Now, all right, you got to integrate this, and we're also going to be taking the limit as b goes to infinity of from 0 to b of e. Well, maybe I stick the t in front. How's that? T times e to the negative s t dt. Yeah. Okay, so we can integrate this. You got to use integration by parts. Integration by parts, ultraviolet voodoo, right? Or, and this says one of them is algebraic and one of them is a loop-de-loop, so you can definitely do tabular. So that's what I would do. T, and then the derivative would be 1 and then 0. E to the negative st. Remember, again, this is with respect to t, so the s is like a constant. Antiderivative of this guy would be another e to the negative st, but chain rule would have said times negative s, so you've got to undo that. And then do it again, antiderivative, which would be an e to the negative st, but times another, so you got to undo that one again, and so you end up with 1 over s squared, a positive 1 over s squared. Now, and then it's a plus and then a minus. All right, so this ends up becoming, another page. This ends up being the limit as b goes to infinity of, it'll be a negative t over, or maybe since I'm plugging into t, I guess I'll leave it separate. Okay, so negative 1 over s, because that's a constant, right? T times e to the negative s t, and then minus 1 over s squared e to the negative s t. And we're going from 0 to b. Yeah. All right. So now, again, limit as b goes to infinity, and you're plugging the b into t. So you'd have a negative s b, right? And then, but here it's a negative, an e to the negative sb. So that does zero out because its e is down in the denominator, and you're taking as b goes to infinity. And so that one ends up being a 0 minus, oh, same thing happens there too, minus 0, nice, minus, because again, when you're plugging that 0 into t, yeah, no, b into t, limit as b goes to infinity. Those were zeros. Okay, now we're going to plug in the 0. Plugging 0 into t here, that'll give you a 0 minus 1 over s squared, and then e to the 0 when you plug it into that t. Yeah. All right, so you end up with a 0 minus a negative, so you end up with a positive 1 over s squared. Now, for what values? Well, for when you your t needed to be you need to keep this negative here, right? For when you plug that b in, and so s needs to be a positive number. If s is negative, then it changes that to be, when you plug b in there, you would be doing e to the infinity. So it's for when s is greater than 0. All right, let's look at one more. This time it's going to be a piecewise function. And we're going to say it's t for when t is between 0 and 1. And it's a 1 for when t is greater than 1. Okay, so by definition, this L of, well, I guess I'll write f of t. Remember, it's by definition, it's this improper integral of e to the negative st times f of t dt. That's by definition what it's equal to, right? But now it's a piecewise function. Yeah, and our t's are going from 0 to 1, and then from 1 on, or 1 to infinity. So we're going to separate this. This is going to be 0 to 1 of e to the negative st, and then your f of t when you're on from 0 to 1 is just t, so times t dt, and then add it to, now to when t is greater than 1, that means from 1 to infinity, of e to the negative st, and then times a 1, and then dt. Yeah. All right, so now I already integrated this from the previous example, right? Can I slide? I mean, the limits were different. Can I get it all the way up there? Here we go. T e to the negative st, we did this tabular, and we ended up getting this guy. So I'm going to just, I'll write from example 2, but the only difference is, so you could do tabular again, but it's a negative 1 over s t e to the negative st minus 1 over s squared e to the negative st. Okay, and then the difference now is it's going from 0 to 1. But we did that whole tabular thing, so I'm not going to go through that again. But this is from example 2. We got what that integral was. Okay, then plus we're going to take the limit as b goes to infinity of antiderivative of e to the negative st is just e to the negative st, but then chain rule would say divide by the negative 1 over s. Make sure that that's obvious that that's a negative there. Okay. And we're going from 1 to b. I did 2 steps in one there. Hopefully you're okay with that. I didn't want to have to write it again. Okay. So we're going to plug in a 1 first into t. Remember, these limits are going into t as if it was with respect to t. So when I plug in a 1 here, I'll have a negative 1 over s times 1 times e to the negative s, and then a minus 1 over s squared e to the negative s times 1. Plugging in a 0 into t will give you a minus, we'll have a 0 here, and then a minus 1 over s squared. E to the 0. Make sure I don't make a mistake. Okay. And then we have plus. So that was the first guy. That was this one. And now when we do this one, when you plug in a b into t here, you'll have e to the negative b. And as b goes to infinity, that will be a 0. And then subtract from that, plugging in a 1 into t, and you'll have the negative 1 over s e to the negative s times 1. Yeah, okay. All right, so this ends up being a plus, whoop, whoop, and we've got a negative 1 over s and a 1 over s, and they both times e to the negative s, so bye-bye, bye-bye. That's nice. So you end up with, and can anything else? I don't see anything else. So it's a negative 1 over s squared e to the negative s plus, is minus a negative, 1 over s squared. Yeah. And that is for, what do we care about? We care about when I plug that b in as it goes to infinity, right? I need this to be a negative, and so this is also for s greater than 0. All right, so that's just practicing with the whole definition of the linear transform, or Laplace transform. I made a slip there, but that's okay, because actually the Laplace transform is a linear transform. The linear transformation. And do you remember what that meant? That meant that when I take L and I do the Laplace transform on two functions added together, it's the same as taking the Laplace transform on F and the Laplace transform on G, and then adding those together. The other part of the linear transformation is that when you do the transformation on a constant times the function, it's equal to the constant times the transformation of the function. So those two things are true. Lovely. We're going to use those for sure. Okay. So we did by definition, right? L, the Laplace transform on e to the at. And it turns out you're going to just memorize these, or you're going to have them on your little cheat sheet. But it turns out that when you do the Laplace transform on e to some constant times t, it will always end up being 1 over s minus a. We had, which we proved that, right, by doing the definition. When you do the Laplace transform on t to some, we did it on just t to the power of 1, but it turns out if you do it to t to any power, it'll always end up being n factorial over s to the power of n plus 1. All right. So I showed you these guys. It also turns out, which we'll use frequently, is the Laplace transform on cosine of at will be s. over s squared plus a squared. And the Laplace transform on sine of a t will always end up being a over s squared plus a squared. All right, so we're going to use these. These are always true, and we're going to use them to do some examples now. So you'll use those frequently. Have that in front of you so that it makes sense, right? If f of t is 5e to the 2t, and what do we want? We want to find the Laplace transform. All right, well, the Laplace transform will end up being, so L of 5e to the 2t will be, it's a linear transformation. So the 5 is a constant, right? So it'll just be 5 times the Laplace transform of e to the 2t. But the Laplace transform of e to the 2t is 1 over s minus your a is 2. Yeah? So you'll just write it as it's 5 over s minus 2. Boop, boop, boop. Nice. All right. What if your function is 4 times cosine of 3t? Well, the Laplace transform of 4 times cosine of 3t would be, got a constant in front, so it'll just be 4 times the Laplace transform of cosine, where your a is the number in front of t, so it's 3 there. So it's s over s squared plus 3 squared. And that'll just give you 4s over s squared plus 9. Like that. All right. What about when your function, find the Laplace transform of 5t squared? All right, well, this guy is just, can I get it in one screen? I knew I should have done it on separate paper. Darn it. Okay, so we got a 5 in front. We're just multiply it by 5. And then t squared will be a 2 factorial over s to the 2 plus 1. So this is 5 times 2 factorial over s to the 2 plus 1. And so that's what? 2 factorial is just 2 times 1, so that's 2 times 5, so a 10 over s cubed. Nice. If they only just stayed this way, right? All right, how about the Laplace transform on 2 times sine of t minus 3 times e to the negative t? Okay, well, we've got, remember, it's a linear transform, so it's a linear transformation. So when you take it, it'll be the Laplace transform on 2 sine of t, and then minus, well, the Laplace transform on 3e to the negative t. So Laplace transform on this guy is, your a is the number in front of t. Yeah. Hopefully you have it in front of you. I can't make it all on the same screen, but sine of at, so it'll be it's a 1 up there, and then an s squared plus 1 squared. So this is you got a 2 in front, so a 2 times a 1 over s squared plus 1, yeah, and then minus 3 times Laplace transform on e to the negative t. Now your a is a negative 1, and so I like this pen, but it leaks a little bit, so fix it. E to the negative t would be a 1 over s minus negative 1, like that. And so then we've got 2 over s squared plus 1 minus 3 over s plus 1. There's the Laplace transform on that guy. All right, let's do a little bit of a trickier one. Not really tricky, but not super straightforward. That would be, let's do the Laplace transform if little f is 6 plus 4 sine of 2t. So what happens when it's just 6? We didn't do that one yet, right? Well, you got two ways of looking at it. You can either consider, and you'll get the same value no matter what, you can either consider 6 to be 6 times t to the 0, or you can say it's 6 times e to the 0t. Either way, right? Because it's just 6 times 1. So, and either way, you'll end up with the same thing. You'll end up with 1 over s times 6. Yeah. And so your Laplace transform of 6 plus, I'll throw the 4 out here, 4 times the Laplace transform of sine of 2t. This is like 6t to the 0, which is just, remember 0 factorial is 1. You end up with 6 over s, or I'll show it. Okay, so if I do it as t to the 0, then it's 0 factorial over s to the 0 plus 1, whatever. And then 4 times sine of 2t will be 2 is your a, so it's a 2 over s squared plus 2 squared. Yeah, and this is 1 over s, so this is 6 over s plus 8 over s squared plus 4. Okay, so not tricky, but anyway, if you had done it on e to the 0, this one would have been a 6 times 1 over s minus 0. Or this one was the 0 factorial over 8. Either way, you end up with 6 over s on either one, so you can treat it either way. Okay, let's do another one. Why am I doing this one too? Okay, whatever. I guess it's better to have more than not enough, but it's making this a long video. Okay, so the Laplace transform on 5t squared plus Laplace transform on cosine of t is a 5 times, this is a 2 factorial over s to the 2 plus 1. And then this one is a, your a is a 1 there. So it's a s over s squared plus 1 squared. Like that. And then so that ends up just being a 10 over s cubed plus s over s squared plus 1. There you go. All right, let's work backwards now. All right, so now you had lots of practice of finding the Laplace transform. Now let's work backwards and find a function, little f, whose Laplace transform I give you. So if I give you, we're going to find function f of t, right, whose Laplace transform is big F of s, whose Laplace transform is given. All right. All right, so if big F of s is 1 over s minus 5, well, that should be pretty easy. All right, you can totally see the pattern, right? It's s minus a. So that means that your f of t, little f of t, will be e to the 5t. Yeah, easy peasy lemon squeezy, right? All right, how about if the Laplace transform is 4 over s squared plus s. All right, well, I don't see a pattern at all. This guy has, this is a constant up here. Okay, so I have that. I have a constant there, but I don't have 16 right there, which is what I would need for it to be signed. So it's not following any of the patterns. So here's what you'll do. You are going to factor the denominator. So it's an s times an s plus 1. Still not helpful, right? Because I need to separate these into separate fractions. You're going to use partial fraction decomp. Yay. Okay, so remember you do 4 over s times s plus 1 is equal to a over s plus b over s plus 1. Multiply by the common denominator, or multiply both sides by this common denominator. So you get a 4 is equal to a times s plus 1 plus bs. It's a bunch of BS, right? All right, and then you're going to let s equal -1, which will give you a 4 equals negative b. So b is equal to -4. And you're going to let s equal 0 to give you a 4 is equal to a times 1 and then plus 0. Okay, so that means that this guy is equivalent to a is 4. So 4 over s plus a -4 over s plus 1. Yeah? All right. Do we see the pattern now? You know, the 4's at top can just be factored out. So this is like 4 times 1 over s. Well, that just means that it's equal to 4 times either t to the 0 or e to the 0t, and then a minus 4 times e to the negative t. Again, checking out these patterns, right? -4 over s plus 1. You have a 1 over s plus 1, right? So you can just factor out that -4. And then also the 4 over s. It's like there's a 0 here. So that works too. Okay, so there's that. How about another one? Geez Louise, there's a lot of examples this time. Okay, what if the Laplace transform is 12 over s squared plus s minus 2? Yeah. Factor that bottom. You got a 12 over s plus 2 times s minus 1. Do partial fraction decomp. Make it a over s plus 2 and b over s minus 1. And so you'll get that. And if I let s equal 1, you'll have 12 is equal to 3b. So b is 4. And when you let s equal a -2, you'll have times -3. And so a is -4. All right, so your big F of s is a -4 over s plus 2, and then plus a 4 over s minus 1. This was an easy example. All right, well then that means that, do you see the pattern? Hopefully you do. You got a -4 times s plus 2, and then a 4 times s minus 1. Easy peasy lemon squeezy. -4 times e to the -2t plus 4 times e to the -1. So a is 1. So it's just a t. All right. One more example on this kind before we actually go and use this. Gosh darn, it's a lot. Okay. What if the Laplace transform is s minus 3 over s squared plus 16. Okay. Well, had this been even then it's an issue. Okay, so nowhere on here do we have an s minus a number on the top. I do have an s squared plus 16. Okay, so I could probably get it to be one of these guys. Yeah. So what you can do with this is you can separate this as s over minus 3 over. Yeah, hopefully you remember that. Okay, so that this is equal to s over s squared plus 16 minus 3 over s squared plus 16. Okay, that's helpful because s over s squared plus 16 takes on this form where if your a was 4, okay, good, yay. A number over s squared plus 16. The number is a there. Okay, so if this was a 4, we could write it as sine of 4t, but that's not a 4, it's a 3. So we just need to do a little bit of algebraic manipulation. Don't you feel like we always are algebraically manipulated things? Because we are, right? So again, this is still a s, because that's not a problem. I can find the function on that one. It's this one that's the problem. I need this guy to be a 4. So I'm going to factor out the 3 out front, right? And if this was a 4, then it's sine. But if I'm going to put a 4 here, do it as long as I divide by 4 also. Tricky, tricky, right? Well, this guy is cosine of 4 squared here, so 4t. And this one is sine of 4t. So we get that this is little f, your little function whose Laplace transform is this guy, is cosine of 4t minus 3/4 times sine of 4t. All right, why doing all of this, right? Because we are going to solve some differential equations with it. Yeah? So let's, first of all, I'm going to give you a note of, if you take the Laplace transform on the derivative of x, it is equal to s times big X of s minus little x of 0. So that's what the note says. What the flip does all of that mean, right? You could think of it too. We were just using big F's and little f's, so I could rewrite this. This just means that the Laplace transform of f prime is equal to s times big F of s minus little f of 0. I wrote big F. I should have written, hold on, let me rewrite that because it's L of F, which is big F, which is S times big F minus F of 0. Yeah. I guess I should have put of S, but anyway, hopefully that makes sense. Yeah. So when we're writing x's because the problem is going to be in terms of x's, but that's just the Laplace transform. That's the original little f, things like that. Hopefully that makes sense. So yeah. Because remember, if you're taking the Laplace transform on little f of t, it ended up being capital F of s. Yeah. And so that means if I'm taking a Laplace transform on little x, it's going of t, right? It's going to be big capital X of s. Hopefully that makes sense. Okay. So let's do an example where they say to us, use Laplace transforms to solve this initial value problem. Now I know there's more than, you have methods of solving this, but we're going to use the Laplace transform this time. Okay, so first thing you're going to do is take the Laplace transform of both sides of this equation. So you've got doing the Laplace, and it's a linear transformation, so we can do the Laplace transform on x prime of s plus 4 times the Laplace transform on x s is equal to the Laplace transform on 8 of s. Took the Laplace transform of everything. All right, well, this guy we know is this. Slide it down. Lx prime of s is s times capital X of s minus x of 0. All right, so this guy becomes s times the Laplace, big X of s minus x of 0. But they gave me x of 0 is 3, so I'm going to go minus 3. Okay, plus 4 times the Laplace transform little x is capital X. Yeah. And then the Laplace transform on 8 is 8 over s. Yeah, remember when we did the Laplace transform on a constant, it would just end up being 8 over s. Okay, I'm going to add the 3 over here. Yeah, and my goal is to solve for the capital X here. So here, I'll write it twice. Okay, so it's s times big X of s plus a 4 times big X of s is equal to 8 over s and then plus 3. These guys both have the X of s in common. I'm going to factor it out, and I would be left with an s plus 4 times big X of s. And then this is like over 1. To add it, I need a common denominator, so this is equivalent to 8 plus 3s over s. I got a common denominator times that, right? Times s times s. Yeah. Okay, dividing both sides by s plus 4, we get that this guy is 8 plus 3s over s times s plus 4. Because I divided both sides. I'm solving for big X, so I divided both sides by the s plus 4. Okay. You need partial fraction decomp to do this. Yeah. So partial fraction decomp. That means 8 plus 3s over s times s plus 4 would equal a over s plus b over s plus 4. Multiplying both sides, we get 8 plus 3s is equal to a times s plus 4 plus bs. I agree. It is. Letting s equal, how about -4 first? You would get 8 plus 3 times -4. So 8 minus 12 is -4 equals b times -4. So your b is 1. And letting s equal 0 will help you solve for a. And that'll be 8 equals a times 4. So your a is 2. Okay, so all of that means that, go to a new page, your capital X, right, your Laplace transform is equal to 2 over s plus 1 over s plus 4. Oh, look at that. And now, hopefully it's very exciting to you, because what does that mean? Capital X of s is this guy, which means little x of t These are capitals. Capital there. Little x of t is, remember 2 over s is just a 2, and 1 over s plus 4 is e to the negative 4t. Yay! That was a lot of work for all of that, right? Well, they also told us to verify it, so let's verify it. Verify. Okay, how are you going to verify it? You need x prime. When I take the derivative of this guy, derivative of 2 is 0. Derivative of e to the negative 4t is e to the negative 4t. Who still has a landline, right? Times, you don't even use it, but whatever. Okay, times. Derivative of this is a minus 4, a negative 4, right? Negative 4, okay. So that's the derivative, and I want to plug that in. Plug into original equation to see, am I right? And your original was x prime plus 4x equals 8, right? So x prime is a negative 4 times e to the negative 4t plus 4 times x was 2 plus e to the negative 4t. Is this equal to 8? It better be, or else we were wrong. So that's a negative 4 e to the negative 4t plus 8 plus a 4 e to the negative 4t. Isn't that so exciting? You go through all that work and it's all right. Love it. Yay. Verified that our solution was true. Okay, that was a long lesson. Hope you all are having a fabulous day. Bye.